In section 3.9, we will solve related rates problems and applied problems involving related rates. Have 6 examples ready for you, and after those 6 examples, I will ask you to try 3.9 daily problem. A stock sells for $80 per share, and its price is increasing by $2 per day. So this one I did type it on Canvas for you, so I want you to try this after this lesson, okay? All right, starting with number 1, or actually talk about what related rates are. Any equation that contains 2 or more rates, and these rates are going to be expressed as derivatives. Is called related rates equation. So for example, take a look. We have 2x dy dt plus 3y equals dx dt. Notice that we have 2 different rates here, right? I have dy dt and dx dt. This is a related rates equation since it contains 2 rates. It has dy dt and dx dt. And if you want to solve a related rates equation, what we're going to do is what we learned last week. We're going to use implicit differentiation, okay? So first 2 examples are just working with equations. And then starting with number 3 all the way to example 6, we're going to solve application problems, okay? So let's try number 1 together. Given y equals 3 square root of x, we want to find dy dt, and they're giving you x is 9 and dx dt is -4. This is a related rates problem because we have 2 rates here. We're trying to find dy dt, but we also have dx dt. Take a look at this equation. I have y equals 3. You know what? I don't like the look of this equation. Why don't I rewrite this as x raised to the 1/2 power? And you know what I'm preparing for, right? I am about to take derivative of both sides with respect to, what do you think? With respect to t. I'm going to do that. Let's take the derivative of both sides, but with respect to t. Why am I doing that? Because if I do that, guys, take a look. What do I have on the left side? I have dy dt right there. Hello, dy dt. And what we're going to have to do is take implicit differentiation on the right side, which you learned last week. And you guys did an amazing job on that 3.8 daily problem, so I know you got it. And you completed that homework too, so thank you for that. Let's take the derivative of 3x to the 1/2 power with respect to t. So use the extended chain rule. I'm going to have 3 and 3 over 2 x to the -1/2 power, right? But use the chain rule. Take the derivative of x with respect to t. What's that going to give you? You're going to get dx dt. So this part, what we just did, the second line, is the implicit differentiation skills that we learned last week. Now, we're almost done. Now, I'm going to go ahead and highlight a couple things for you. We were given x is 9. There is x right there. What else we were given? We are given that dx dt is -4. So here's dx dt right there. So what do we have to do now? You just have to plug in these values. They gave it to you. So what's dy dt? That's going to be 3/2 times 9 to the -1/2 times dx dt is -4. Let's simplify this. This is the same thing as 3 over 2 square root of 9 times -4, right? All I did was I sent that 9 to the -1/2 power to the bottom of this fraction and just rewrote raising something to 1/2 power as taking square root. So I know you're okay there. 3 over 2 times 3 times -4. I can see that 3's will cancel out right there. And my final answer, not final yet, I'll have -4 over 2. Therefore, my final answer is -2. So that is dy dt when x is 9 and when dx dt is the change in x in terms of t is -4. So we're going to apply this in some of these applied problems in example 3 through 6. But this is the idea. You get an equation, you take the derivative of that equation implicitly, okay? And then you're going to plug in the values they will give you. And that's how we answer these questions. Let's practice one more, just equation, okay? So given y equals, now this one I got it from your homework, number 1. Given y is 2x squared plus 7x, they want you to find dy dt. And they're giving you x is -1 and dx dt is 5. So what do you do first? Write down your y equals 2x squared plus 7x. But we are going to take derivative of both sides with respect to t, because I want to create dy dt. So I'm going to go ahead and take the derivative of both sides with respect to t. So what's the left side? The left side is dy dt. The right side, we have a sum. I'm just going to go ahead and separate these. d dt of 2x squared plus d dt of 7x. You ready to do implicit differentiation with me? All right, so the first one, we're going to get 4x to the first power times what? Dx dt. Plus the second one. If you take the derivative of 7x, I'm going to get 7, but don't forget to multiply this by the derivative of x with respect to t. So we're going to get another dx dt. All right, now time for us to plug in what they gave us. Remember, they said x is -1. So everywhere you see x, that's what you're going to plug in. Now, what else did they give you? They also gave you dx dt is 5. So let's go ahead and substitute these values they gave us. 4 times -1 times 5 plus 7 times 5. And that is what dy dt is going to be. So let's go ahead and evaluate that. The 4 times -1 times 5, I'm going to get -20. And I'm going to get 7 times 5, 35. If I add them, my final answer is 15. All right, not bad, right? Okay, so hopefully you understand how to do the ones with just equations. What I'm going to do with you now is some application problems. And sometimes they don't give you the equation you need. Like, you see how it was very helpful? They gave you, hey, here's your y. Or, hey, yeah, if they give you the function, then we just take the derivative with respect to t and then went on about it. But sometimes they won't give you the equation. Like number 3. They will assume that you know the area of a circle equation, and we do know that. So we're going to try example 3, and we're also going to look at the volume of a cantaloupe, but that one, they gave you an equation. So let's go over example 3 together. A colony of bacteria in a petri dish forms a circle whose radius is increasing by, let me go ahead and highlight something, whose radius is increasing by 0.7 millimeter per minute. Now, what they just gave you in word is the change in radius with respect to time, isn't it? So in symbol, what's that? That's dr dt. Change in radius with respect to time. And they gave you that's equal to what number? 0.7. Now, I'm going to keep that number there because I will be using it soon, right? All right. What they want is this. They want you to find the rate of change in the colony's area at the moment when its radius is 12 millimeter. Let me highlight one more thing here. Radius is 12 millimeter. What are they giving you? They're giving you that r is 12. Now, remember, on our previous examples, what I highlighted in orange and pink, those are the numbers that we've plugged in after taking implicit differentiation, right? We'll do that too. So if you have a word problem, they're going to give you the rate of change, and they're going to give you what value to kind of plug in. So that's what we need to keep in our on our side over here. I'm going to keep this over here because once I'm done taking the derivative of this area formula, I'm going to go ahead and plug them in, okay? All right, you ready? So let's go ahead and write the area of a circle first, which they didn't give to us, but we know what that is. Area of a circle is what? Pi times r squared, isn't it? So what I'm going to do is I'm going to take the derivative of this area function with respect to time. So then I'm going to get d dt of area equals d dt of pi r squared, right? That's what I'm doing right now. So the left side, I'm going to write that as derivative of a with respect to t. So how fast or how is the area changing with respect to time? And that's what we are asked to find, right? Find the rate of change in the colony's area. All right, it's growing because the radius is getting bigger, right? But how fast is it growing? That's the question. So let's take a look at the right side. Now, take the derivative of pi r squared with respect to t. So remember, pi is just a constant. So I'm going to bring down that exponent of 2 and have 2 pi r. And we're going to multiply this by what? The derivative of r with respect to time. And that is dr dt. See, they say like this section can be omitted without loss of continuity, but I wanted to do this with you because you guys worked on implicit differentiation last week and we had so much fun with it. I want to actually use it to solve some applied problems. So 3.9, I didn't want to skip. All right, so let's go ahead and plug in everything we have. So if I plug in 2 pi, remember the radius they gave us was 12. And remember, dr dt, the radius was increasing by 0.7 millimeters per minute. So I'm going to do that. And I will use my pi button on my calculator because I think instead of 3.14, because you want to be pretty accurate in your answer when you're typing this in your homework. All right, I took a picture of this real quick so that I can get out to the calculator app. Where are you, calculator app? All right, here we go. So I'm going to go ahead and type in 2 pi. Do I know how to type in pi symbol here? You know, these little things. Maybe I'm looking at it. It's right by the caret button. So I'm going to do 2 pi times 12 times 0.7. And I think that's exactly it. Yeah, okay, now I'm about to hit enter. And the answer is 52.778756. So, all right, let me go out to my paper. And then write down how did they want us to round it. They really didn't say how to round it. So I'm just going to round it however I like. 52.78. So the area of this bacteria colony is growing by about 52 what's the unit though? This is area, right? Square millimeters per minute. At the moment, its radius is 12 millimeters. And that's how we answer this question. All right. So hope you're doing okay. Now we're ready to go in and take a look at the next one, the volume problem, okay? Volume of a cantaloupe. It's a sphere, right? It's a ball. It's approximated by volume equals, they gave us this equation. I remember, using that in a geometry class, but now we're going to use it in a calculus class. The radius is, growing at a rate of 0.8 centimeter per week. Our melon is getting bigger. So let me go ahead and write down what they just gave me, okay? The radius is growing at a rate of 0.8 centimeter per week. How would you write that in a symbol? I'll say that is dr, change in the radius, with respect to time, and time here is week, right, is equal to 0.8. I'm just going to go ahead and write the numbers in. Okay. At a time when radius is 6.6 centimeters. So I also have that r equals 6.6. Now I write these down because I know I'm going to write them off, plug them in later when I take when I do implicit differentiation of that volume of a cantaloupe equation. All right, so what's the equation? Volume equals 4/3 pi r cubed. And you know what we're about to do to both sides, right? Let's take d dt of both sides. Take the derivative with respect to time. Okay? How fast is my volume getting bigger, or is the volume changing? Not volume, cantaloupe. So dv dt, the change in volume with respect to time, is equal to, now let's take the derivative of this slightly intimidating looking equation, but 4/3 pi, you know that's just a constant. So if you use your applied chain rule here, or extended chain rule here, the 3 will come down and this 3 will come down and get multiplied by this 4/3, right? So you will get 4 pi radius, what's the new exponent? Squared. Now you're going to multiply this by the derivative of radius with respect to time, so dr dt. Whew, we got it. Now let's plug in everything we know. It's a one-liner. 4 pi times, what was the radius they gave us? 6.6 squared. And then I'm going to multiply by the rate that the radius is changing with respect to time, which was 0.08. Alrighty, I'm going to go ahead and type this in my calculator. Oh, oopsie, excuse me, let me close this. All right. I'm going to go out to my calculator app. Close. Type in 4 pi times 6.6 squared. Get out of the exponent and multiply this by 0.8. When I did that, I got 437.91. All right, let me go and write that answer down and put some right units there too. Okay, so how fast is the volume changing at that moment? Oopsies. 437.91. And let's be careful about unit. This is volume, right? The radius was given in centimeters, so this will be cubic centimeters per week. And this is positive. I think, one thing that I didn't like about my examples today is all of them are growing. They're getting bigger. They're increasing. But I think there's one problem that you're going to do for me. Or maybe example 6 is, we may have a decreasing too. So it doesn't always have to come out to be positive. But in the melon case, we want it to grow every week. So that came out positive. All right, I got a couple business examples to go over with you. Just example 5 and 6. And I'm going to go ahead and ask you to try 3.9 by yourself, okay? Now let's look at this business example together. First, number 5. Rates of change of revenue, cost, and profit. Okay, for loose landscaping, the total revenue and the total cost in dollars for yard maintenance of X homes are given by revenue function is 1,000x minus x squared, and the cost function is 3,000 plus 20x. All right, suppose that loose is adding just 10 homes per day. Okay, I'm going to go ahead and highlight this. 10 homes per day. So, we should probably try to give some variables here. How about I call this the information that I'm just given? I'm going to call this dx dt. The number of homes, the change in number of homes with respect to time, and time here is day, is equal to positive 10, right? Adding. Loose is adding 10 homes per day at the moment when the 400th customer is signed. So X is equal to what number? 400. That's the number of homes. At that moment, what is the rate of change of A? First, total revenue. B, total cost. and C, total profit. Now notice they gave us the equation for total revenue and total cost, but what's the total profit? Well, you do know how to find it. Total profit is going to be, remember, revenue minus the cost. So let me go ahead and write that down for you right here. We're going to say the profit, I'll say P of X. Profit at X number of homes is equal to revenue at X number of homes minus the cost at X number of homes. So you know what? We're doing related rates problem for actually 3 different equations here. Let's go ahead and find total revenue, the change of total revenue at that moment first, okay? So A, the revenue function is R of X equals 1,000 X minus X squared, right? Now, let's take derivative of both sides with respect to time, okay? So, dt of both sides, dt of both sides. You know what? I'm going to go ahead and just rewrite at the left side as well, dr dt. That's what it is. Dr dt is equal to, now let's take implicit differentiation on the right side. So what's that going to be? We're going to have 1,000 times dx dt minus 2x times dx dt, right? And now we're going to plug in the values that we were given. Now remember, dx dt is 10 and X is 400. So, because Luz was interested in that very moment when he was adding 10 homes per day and when he had 400 customers signed. So let's plug in everything we know into this dx, this X, and this dx. All right, so that's going to be 1,000 times, what was dx dt? 10 minus 2 times X is 400. And then we're going to multiply that by dx dt of 10. All right, I may be a little out of room here, but go ahead and type this in your calculator. If you plug this in, you will get about exactly $2,000. And what's the unit? What's the time unit? Day. So this is how his total revenue is changing per day. And that was part A. Let's go ahead and go over to the total cost. B. Total cost function is C of X. I wish I had more room in this. 3,000 plus 20X. And you know what we are about to do. We're going to take dt of both sides. Take the derivative with respect to time on both sides. So if you do that, that's going to be what? dc dt, the change in cost with respect to time is equal to, now what happened to that 3,000? That's just a constant, so that's just gone. No more 3,000. But we're going to have 20x. If you take 20x with respect to, we differentiate it with respect to time, we're going to get 20 times dx dt. Now this one came out kind of easier. So if I plug in what dx dt is in here, I'll get 20 times dx dt of 10. So it came out to be $200 per day, and that is the rate of change of total cost. Now let's go ahead and figure out the profit. Now, profit, I don't think I'm going to have to do all this because we do know what profit is. Profit is simply revenue minus cost, right? So I'm just going to subtract. But let me just make a little more room over here. So C, finally C. I'll say that dp dt, and P stands for the profit here, right, is equal to revenue minus the cost. So I'm going to go ahead and subtract my dr dt, what I found in part A. And I will subtract dc dt, the cost with respect to time, the change in cost with respect to time. And that's going to be what? That was 2,000 for the revenue minus 200 for the cost. So therefore, here's what we got. The profit is changing at $1,800 per day. So this was one of the business application problem that I wanted to go over with you. And we're almost done. We just got the very last one. The last one is about stock and how the price of share is changing. And this last one, I think is very similar to the one that you're going to do for me. I just thought I thought the daily problem for today is it's kind of fun. It's challenging. I want to give it to you. You may have to solve it backward, but I'll ask you to try it because I think I didn't challenge you enough last week. I think you guys just found it a little too easy. So I want to give you 3.9 problem today after example 6. So this will be my very last example in 3.9. So let's take a look. Suppose that in a highly volatile market, 10,000 shares of stock have been sold at $45 per share, and that the number of shares sold is increasing by, oh, you know what I like? I'm going to highlight this. The number of shares sold is increasing by 150 shares per day. What did they just give us? They just gave us one of the rate, right? They gave us that the rate, that the number of shares is selling is increasing by $150 per day. I'm going to have to assign some variables over here. So let me go ahead and do that. What I just highlighted in green, 150. I'm going to go ahead and say, what letter should we, let me go ahead and write down the variables here. How about we call the price, let P equal the price in dollars. And then I'm going to say the number of shares. I can use N, but let me go ahead and use Q for the quantity sold, okay? So what's the revenue? The revenue, because they're going to be asking for it. While the total revenue is decreasing by $18,250 per day. And what is the rate at which the price of a share is changing? So we are asked to find this part right here. What is the rate at which the price of a share is changing? We're asked to find dp dt here. The price is changing, yes. So, but we were given what the first rate is. The number of shares sold is increasing by 150 shares per day. So that highlighted information gives me this. I know that dq over dt, the number of shares, the quantity sold is increasing by, and it's increasing, so I'm going to go ahead and write 150. So that's what we have. But what they want here is what rate at which the price of a share changing. They're asking you to find dp dt. That's what they're asking you to find. And there is a third of information they gave you. They also gave you that the total revenue is decreasing by $18,250 per day. So let me go ahead and write that down. And is it okay if I use dr dt for this change in revenue? I'll also say, I'm going to highlight this information. Total revenue is decreasing by that much per day. Now, for the first time, we have a negative rate. So I'll say dr, the revenue is changing at negative 18,250 per day. So that's what we were given. And guys, I wrote down everything that we were given, right? So we need to find dp dt. And I'm going to give you an equation. Just like how for the area of a circle problem, we needed to know that area is equal to pi r squared. And for the volume of a cantaloupe problem, we needed to know that the volume is equal to 4/3 times pi r cubed, right? Now, they didn't give you any equations, so we're going to go ahead and write down that equation that we need. I'll write down that the revenue is equal to the price in dollars for each share, the share price times the quantity sold, okay? And now for the first time, we're gonna be using, well, in this section at least, we're going to have to use the product rule to differentiate that equation. So what we're going to do to both sides is, let me write this down. The revenue function is the share price times the quantity sold. Take derivative with respect to time on both sides. This is exciting. If you do that, the left side is dr dt, right? And we usually found that, but they gave that number to us. So, later on, I'm going to plug in that negative 18,250 into the left side. But let's go ahead and work with the right side. Because, unfortunately, we're looking at a product of P times Q, right? That is P times Q. So, let's use the product rule. Let me go ahead and write down that we're about to use a product rule here. A quick review of product rule is FG prime plus GF prime. Okay, so let's do that. Let's get at it. So derivative, first write down P, and then we're going to write the derivative of the second one, which is Q, and that is going to be dQ dt plus G, which is Q, and we're going to multiply this by the derivative of the first term, which was P. So that's going to be dP over dt. All right, now, I hate how my Q looks like 9. How can I make Q look more like Q? Does that look like a Q? Okay. Now, we do have everything that we can plug in. So let's start plugging in everything. The left side, what is dr dt? That one was given right here, dr dt. Negative 18,250 equals. Now, did they give you what P is? Did they give you what P is if you read it? Yes, they did. They gave you that the price of a share is, I didn't highlight that information, $45 per share. So P is 45. And we wrote down dQ dt is 150 plus Q, what was the quantity? What was the quantity? Oh, here it is. 10,000 shares of stock. So that was the quantity. 10,000. If I just look carefully, it's all on my paper, huh? Times, but the last one, they did not give us the change in price with respect to time. That's what we are solving for, right? So we're going to go ahead and solve this equation for dP dt, and that's going to be our answer. So left side is still 18,250. If I multiply 45 times 150, 6750 plus 10,000 times dP dt. I can make this a little bit smaller if I can. Oh gosh. Give me 1 second, guys. I'm trying to figure out. I needed more room for this. I'm gonna make this guy a little bit smaller, or maybe over there. Oh no, I took my parentheses. You're looking at me playing around with my... Okay, and then I'm gonna minimize this a little bit, okay, so that I can have one more line to solve this. Thank you for your patience. Okay, subtract 6,750 from both sides. If you do that, what will you get? The left side will give you negative 25,000. And the right side is 10,000 times dP dt. So finally, if you divide both sides by 10,000, dP dt, the change in share price, the price of a share is actually negative. It's going down by negative 2.5. So what we can say is we found the answer. Thus, the price of a share is decreasing at a rate of $2.50 per day. That is it. Whew, that one was kind of fun. it was slightly different, don't you think? Because I had to plug in the numbers they gave me. I had to be very careful about what is what. And it was helpful that I labeled my variable as what it is. I said, I'm going to say P is the price in dollars. I'm going to say Q is the quantity sold. And clearly said that revenue is simply P times Q. And just went and did the implicit differentiation and plugged in everything. Try this for me. I wanted to give you something a little bit fun for 3.9 problem. So I want you to try 3.9 daily problem now. And because I want to be able to finish everything this semester, I still want to, I'm going to go ahead and come